right, slingshot projectile.
Go.
Here we have a makeshift slingshot that will project this ball, which will be our projectile. Here's our starting point, measured out and marked with pencil. And this is where we'll begin to measure a range from this position to where it lands here on this poster board.
1, 2,
so,
3. I hit that one.
And that's where our projectile landed on our poster board. And from that, we'll have a measured range and a measured height from the bottom of the ball to where it lands here on the poster board. And with that measured height and range, we should be able to figure out the initial velocity of our projectile. All right, here we're gonna do projectile motion with a consistent velocity using a dart gun. So most of these are inexpensive, under $10. This is a Nerf dart in here, loaded, and we have over there set up some paper on the ground so we can mark our spot. And the important details we need in this demo and experiment is to get the height from which we fire our projectile. So I'm going to try and keep this level with the height of the table. The bottom of the dart is going to hit the paper here, so we want to measure the range from this height, and we want to measure the height and we want to measure the range, excuse me. So to get the range, so we want to mark the paper, so I'm going to dip my dart in a little bit of water here. Okay, so I'll get a paper marked. I'm going to keep this level, this dart gun level with the table, and I should get a range marked on my paper. Now I'm going to do this again, and I want to do this 3 times so that I can take the average of all 3 of those range units and get a better idea what my initial velocity is.
Just make sure and wet it.
Okay, so it looks like I didn't get that one wet enough, so I'm going to do it again. Okay, putting it into the dart. Pull the trigger. Make sure I am at this edge of the table so I can measure my range correctly. And fire. Here's our mark. So we'll measure the range from this point. It's a small little wetted dab. Actually easier just to put your finger on there and you can feel it. And measure that. So we'll call that R1, our first dart hit. And we want to do this, repeat this for at least a total of 3 times so we get a variety of range values. Nice shot. And it should be right around our other range value. Here is our standard ballistic pendulum, and we're doing a little short demo on projectile motion with this ballistic pendulum. This is one of the devices we use for our labs, and we have students work with the ballistic pendulum. We have them take measurements to figure out what the initial velocity is and the time of flight is for this ballistic pendulum. Now, the data we need here is we have here our actual pendulum that is compressed. The spring compresses here so that it shoots off this metallic ball at a certain velocity. So it's a consistent same initial velocity each time. So it'll fire this ball, and what we want to do is we want to make sure that we take a measurement from the ground to the bottom of the ball. Okay, so here I have about 96 centimeters. So I have 96 centimeters from the bottom, from the ground to the bottom of the ball, and that will be the height, the initial height or the initial position, vertical position of the ball. And what I want to do then is project, get this ball into motion, and find out where it's going to land on this paper. Now what we have here is carbon paper, which will mark the spot for which it lands. And when I get that position, then I'll measure the position from that ball to where it was released. Okay. So I look for the bottom of the ball measurement, and that will be my range value. So when I have the horizontal position, or the range, and the vertical position, I can use those numbers to find the initial velocity and the time of flight. Okay. Are we ready? Okay, ready to fire. Projectile motion with the ballistic pendulum. And here we have, come up a little closer, or can we sit there? Here we have a hit right here. And that's another meter stick. So we got a range of 2 meters out of this. Now, like any science experiment, what we want to do is repeat and see if we could get another measurement for a range. And the more range values we have, then we could average out the range values and get a better value overall as to where the ball will land and what we could use to estimate our time of flight values and initial velocity. All that we used in the pendulum, so you can see where it struck, and this is the position for where we want to measure our range from. Projectile ballistic pendulum physics, and we could do some kinematic equation solving for unknowns with it. Projectile motion with a catapult set at 45 degrees. Let's analyze the flight path of this glow ball. Now let's change it to stop that clip.
That's right here, boy.
Angle of elevation, 35 degrees. Angle of elevation, 25 degrees. Angle of elevation of 15 degrees. Seth, what you got there?
Catapult.
And what does the catapult do?
Shoot the ball. And we're trying to make the ball into a can, which
It
pretty much
is.
impossible.
It's sort of far away, huh? It's not impossible. It can be done. We're ready, Dr. Seth. Fire at will. Whoa, that was so close. It's a little hard to get that in there, though, isn't it?
Yeah.
Okay, thank you, Dr. Seth, for your catapult expertise. Let's see, how high is the ball from the ground?
About
15 centimeters?
Yeah, that's about how high it is.
Okay, we got 15 centimeters. And then we're measuring the distance from here to the target. And before you fire, Mr. Seth, I got to do one more thing. I got to measure something called the angle of elevation. And that's the angle that this arm is at. So it looks like it's almost completely horizontal. And we could find out by measuring with a protractor. So this thing right here measures angles. And let's go ahead and measure the angle here. All right. What we have, can you put the ruler here and see how flush it is? Let's see.
This is what she's talking about.
That's the protractor.
You guys don't know.
That's a protractor, right? And it measures the angles, but we got to see how flat the ball is compared. Now, is the ball like hanging downwards here?
Kind of.
It is, huh? It's sort of at an angle. What angle is that at? Could you hold this for a minute, Seth? Hold that like that. Good, thank you. And what we'll do is we'll measure our angle. Hello there, physics folks. With me is my assistant, Mr. Ulysses Call, and we're trying to determine his pitching speed. And he's going to pitch this baseball out horizontally, so it has no vertical velocity components from a certain height. So to show us where you're going to hold the ball. Okay, we're going to measure that from the ground to see how far above the ground the height of the baseball starts. And he's going to pitch over there to the net, which will catch the ball, and it'll be a little lower above the ground. So we'll mark where it's going to hit on the net. And with us there is our assistant, Seth. Hey, Seth, Dr. Seth. And he is going to estimate the pitching speed with the radar gun. However, what we're going to do is we're going to try to calculate the pitching speed using the height above the ground to start, and the range value, and the height above the ground for which the baseball lands. Okay, are you ready? I'm gonna
Should I do my pitch wind-up or should I?
go ahead and pitch us a ball. Now we're going to measure the distance from where our pitcher stood to where the ball landed in the net over there. Okay, so our assistants are going to help us in this feat. All right, go. Oh, physics audience, we're going to go through some 2D motion in this short video clip, 2D motion, and the special case of two-dimensional motion, projectile motion. what we're doing is we're doing a little background to a lab that we do, an online lab for a physics college section. And this lab deals with two-dimensional motion and the special case of projectile motion, where the only acceleration is due to gravity. So in our lab, we have going to have two parts to it, which I'll run through. The first part is some standard two-dimensional projectile motion simulations that are online to grab our data from and to figure out some unknowns based on the knowns that are in the simulations. And the second part is some do-it-yourself exercises, activities. Most of these involve like having a horizontal velocity only and doing some measurements to figure out what the initial velocity is, and so on. So we'll look at these in a little bit more detail after I run through some general outline ideas based what this lab is based on. Okay, so in general, we looked at 1D motion. Now what we want to do is really understand the two components of motion when we're looking at two-dimensional motion and applying our kinematic equations, which only are applied for constant acceleration problems. So we're going to restrict ourselves to the cases where the acceleration is constant, where we can use the kinematic equations. What we have to be aware of is the two sets of equations that we need. We're going to need kinematic equations for all our x motion or horizontal motion, and we're going to need kinematic equations specialized just for our vertical motion. So what we want to look at is 2D motion in general with constant acceleration. We apply kinematics to two directions, which are going to be our horizontal components of motion and our vertical components of motion. And for any of these problems that are constant acceleration, deal with two-dimensional motion, you always want to break down the motion horizontally and break down the motion horizontally and break down the motion vertically. Okay, so it's a good idea to list your components and get your notation straight. So for horizontal components of motion, we could start with any one kinematic equation, like delta x equals Vx naught t, and then what we have as well is plus 1/2 ax t squared. Okay, so that's one of your kinematic equations. And remember that this is x final minus initial, so x minus x naught, or if you use the x final minus x initial notation, that works, equals v, the horizontal initial velocity, times t, your time of flight, or the time that elapses, plus 1/2 acceleration in the x direction, t squared. Okay? Then you repeat that for your second kinematic equation, which you could use, let's say, v equals v naught plus at. But this is specific only to the horizontal direction, so we would say vx naught plus axt, and then continue with these kinematic equations for the other two that you could use. Okay? So this is just the horizontal part of the motion that we want to analyze, and it's good to outline it in any 2D problem at the very beginning. It will help you put your problem into perspective. And then we lay out our vertical equations of motion, which would be delta y in this case equals vy naught t plus 1/2 AT squared. Okay, and I'm going to say this is acceleration in the y direction, and my y is going to be y final minus y initial, or y minus y naught equals vy naught t plus 1/2 ayt squared. And the second equation, this would be specific to just the y motion. Dot, dot, dot. Okay. So get as much information, put this all out in your problem, and then plug in your knowns and see what your unknowns are to solve the problem. Now, in the case where you know the acceleration is only due to gravity, in the 2D special case, projectile motion, which is what this lab deals with, the only acceleration is due to gravity. Okay? So your equations, your motion equations, break down to in that case, we could say our horizontal motion and our vertical motion can be looked at in this way. So horizontally, if it's projectile motion, which means this applies to flying darts, dart guns, bows and arrows, any sort of projectile that you toss out that has some sort of horizontal velocity, like a baseball. So if I throw a baseball up in the air and it lands, it has both a horizontal component of motion and a vertical component of motion. But in that case, the only acceleration once I release the ball is due to gravity. It's only vertical. So if we look at the acceleration horizontally, that should be 0. You should have a constant horizontal velocity, and what we're doing is ignoring air resistance, which might change that fact a little bit. So AX is equal to 0. Now if we look at the vertical, the horizontal motion for velocity, Vx will be its component velocity vector with respect to any angle for which that object is projected. So our horizontal velocity equals a V naught cosine theta. Its component of velocity, initial velocity times t. Okay. And then also, not times t yet, so that would be our horizontal velocity, and then our horizontal position coming from this kinematic equation. Okay, so in that case, this is 0, so we have no acceleration horizontally. So all we'll have is x. Our final position will be v naught, our initial velocity, cosine theta, so that we have our horizontal velocity only times t. So you could break down your horizontal motion into these 3 pieces, these 3 definitions, and apply that to your problem. Now, in the similar fashion, we could break down our motion vertically. In projectile motion, our acceleration along the vertical axis is only due to gravity. So we have acceleration due to gravity. So AY is equal to minus g. And our vertical velocity is the vertical velocity component vector, which is Vy equals V naught sine theta. Okay. And then what we also have is we have the minus gt factor that plays a role here, because that's going to change that vector at any point in time. Okay, we'll look at how the vector diagrams are done. And what we have also is our position, our vertical position now is going to be based on this kinematic equation. So we're going to have our initial velocity component component, V naught sine theta t, and then we're going to have plus 1/2, in this case minus, because the acceleration due to gravity is downward by my convention of positive upward, positive to the right. So this will be minus 1/2 gt squared. Okay, so I laid out all my motion quantities in the vertical direction. So what you want to do again is plug in any knowns that you have in a problem and then use these to find your unknowns when you know it's projectile motion. So one other note, what you have to remember is that your starting velocity, if you're starting from the ground and your projectile hits the ground, those two velocities should be the same, the initial and the final velocity, as long as the elevation is the same from which the projectile fires and lands. So note that V total should be Vx squared plus Vy squared. Okay, that should always happen. The total velocity at any moment in time of a projectile is the combination of the x and y component velocity vectors. Okay, so a few more points to make here. Is the vector parts can be very tricky, and you want to make sure that you apply your geometry rules for vector addition and subtraction. So when we're dealing with projectile motion, we have a few terms that come into play. You have the, if I send a projectile outward, if I kick a soccer ball, if I throw a ball up in the air, this is the initial velocity. Okay, and it's broken down into two components, so it has a Vy component and a Vx component. At any point in its motion, Vx, Vy, and it goes up. And what goes up must come down unless it's the escape velocity from the earth. So there is a fast enough speed. So if you were to pitch a baseball really fast and you had a flat surface, no mountains or elevation differences, that baseball should be able to go around the earth and you can send it into orbit, right? Or out of orbit, beyond. You could propel it out into space. So anyways, most people can't throw things that hard. So what we have is objects that are fired upwards come back down. This angle right here is our angle of elevation. Or inclination. And here's our range. And then it should reach a maximum height. And at that maximum height, this is one of these tricky things that are supposed to be known in physics problems. At the maximum height, Vx is still constant, right? Vy is changing. Vy minus g. And at the top, Vy equals 0 at the top. So we have a range, we have an angle of elevation. We're going to have different height values. So these are going to be our vertical distances or our height. Okay. And those terms come into play when you're dealing with projectile motion. So let's take a look at a little breakdown of our lab. And I will show you how to do some vector representation of the problems. Let's guide you through. So even if you're not in this class, if you want to look up some of these simulations, that there are some standard simulations out there to try out, please do. So the first one is dealing with the ball drop versus thrown out horizontally. This is a standard physics demo. So if you have ball, drop, if you're going to drop a ball, like in free fall, what's going to happen is it'll drop and hit the ground. Okay, I'm gonna make a little division here. Okay, so this is our dropping height. This is our height, or y. We could call this y final, y and y initial. And what happens in that case is we know that the velocity vector is changing. Just get a better pen. So what's going to happen here is the velocity, if you do velocity vectors, v1, v2, these should increase by a constant rate, right? So what we know is that delta v, which is in the direction of your acceleration, equals v final minus v initial, which you could say, for instance, like v4 minus v3, if I do the subtraction of vectors, v4, and then I add minus v3 to it. Okay, this approximate distance equals a. Or your minus g in this case, because that's what the acceleration is. So the idea is if I drop a ball, okay, my vertical velocity will change due to gravity, and that gives me my acceleration of minus g. Now, if I were to throw a ball horizontally at the same time I drop it, so I drop one ball and I throw one out horizontally, and my timing is exactly the same, this is what the path will look like. Now we're giving it a horizontal velocity. But one thing about this problem is exactly the same, is that the vertical motion is exactly the same as just dropping the ball. So what we're going to have is we're going to have it move outward with a constant horizontal velocity. And excuse my drawing, I'll get this. I'm trying to show my Vx vectors are exactly the same in size. Okay. So I'm going to label these as V1x. When I have 2D motion, it is wise to notate both the coordinate of that motion, okay, the component of motion that you're working with, and give it a number. So all these are the same. So Vx is constant. So what we know is delta V in this case equals 0, which is why Ax equals 0. Okay. So if I were to say V2x minus V1x, I would take this vector and I would subtract this other vector. They'd be the same size, but in opposite direction. They would cancel out. Okay, so the horizontal motion is the same, but what's going to happen with, I'll highlight this in blue, but the vertical motion, it's going to be exactly the same here. It's just going to be spread out, okay, horizontally. So what's going to happen is we're going to have Vy0, 0, and then we're going to have it slowly, Vy2 will increase some more, and then probably should have drawn this a little further up, but that gives you an idea what's happening. This should be a larger vector. And you can see that you're going to still have the same difference. So in this case, if we look at delta Vy, which equals V minus V naught, and we do Vy4 minus Vy3, we're going to have this difference. I should show this again. We're going to have Vy4 plus minus Vy3 will give you this minus G, or minus A. A, which is minus G. Whichever way you want to notate it. Okay, that's what this first part of the simulation does. The second is the ballistic heart. And this is a standard demo. And what happens in this case, we have one of these in our lab, but the idea is if I am moving with a constant velocity, I throw a ball up in the air, and I'm moving with that constant velocity, I should be able to catch that ball without having to slow down, speed up, or stop, okay? So your horizontal velocity is constant, and by the rules of projectile motion, you should be able to catch that ball. So it's a great experiment to do on your own or to ask somebody else. Well, what do you do? If you're running and you throw a ball up in the air, what should you do? Should you slow down to catch it, stay the same speed, or speed up? So this is a very good classic demo on that. The third demo we have, or a simulation rather, is the projectile lab. And this just goes through a standard projectile. What happens as you change your angle of elevation? How does that impact the time of flight? How does that impact your range? Which angle gives you the maximum range? Which angle will give you the maximum height? So you're going to look at your angle changes and the impacts on X, Y, and T, your time of flight. And the other thing is to note on this lab, that's a simulation, is that you could also experiment with different acceleration due to gravity values. So what comes up in this projectile lab is, okay, if I throw a ball up in the air, whoa, if I throw a ball up, okay, and I catch it, will it reach the same height if I were to do that like on a planet like Mars, where the acceleration due to gravity is about 1/3 of Earth? Well, what's going to happen in that case, if you're on Mars and you threw the ball up, it would go much higher. It would change some of these values. So you could experiment with these other G values. If I were to throw this up on a planet with very large acceleration due to gravity values like Jupiter, what's going to happen is I'm going to need more force to get to the same height, or if I throw it with the same amount of force, it will not reach as high of a value. Okay, so you could play around with your theta changes and your impacts on your positions in time. All right, now the fourth simulation, the fifth simulation, are good standards. The fourth simulation is going to correlate with your do-it-yourself experimentation at home. And the fourth experiment is looking at this relationship between your range and your height. Okay? So here we have a bicycle jumper. And they're going to go off a cliff. And this is cliff jumping Joey. Okay? So we're going to throw this object off a cliff, and this is going to be much like rolling a ball off a table and finding out how far it lands and trying to figure out some unknowns like how long that takes and the initial velocity. So if this cliff jumping Joey is on his bicycle and goes out with a horizontal velocity, so the angle here is 0, that's a trick. So it's going out with just a horizontal velocity. What we want to do is look at this range value and get the ones that are in the simulation, measure those out, and we want to look at this height. Okay, I'm going to use R and H to notate these instead of X and Y. Okay, so the idea next is like, okay, if we lower this, change this height, what's that going to do to our range value? that going to lower our range value or is it going to make it higher? So what we want to do is look at finding our initial velocity and then your range and h relation. Can you form a linear relationship between those two variables using the equations, your kinematic equations that we outlined at the very beginning? So if you make your equations for your range, make your equations for your height, and you relate the two, can you make a relation and find what the slope is, right? So this should really be an r squared versus h relation that you will find based on the data and changing the height position. So you're going to change quite a few height positions. You're going to see how that correlates with a different range. And you could plot those and do a linear plot and find the slope to find that relationship. Okay, so we want to look at those values. So these are some important ideas. So r squared will equal something times h. Okay. And then the fifth simulation, this one tends to be the one that's a lot more mind-bending for students. Number 5 is the tranquilize the monkey simulation. Okay, and there's a few key ideas here, and I've posted some key equations online. In this simulation, what you have is you have a monkey that is out of position by being on the top of a tree, okay? And you have a ranger, let's say, that wants to tranquilize the monkey that's on the top of this tree. So here you have a ranger that will fire a tranquilizer dart at the monkey. And in this classic thought problem, this is a thought experiment, we like to think our concept of physics through and work it out. That's what we mean by a thought experiment. So if this ranger were to shoot this dart, V0 dart, out at the same time, this monkey sees the ranger about to do this and drops. So we'll call that V0 monkey, which we know is 0 initially, right? Then it's going to start really falling. Okay. So as the ranger shoots the dart at the same time this monkey falls, where should the ranger aim to make a hit, target hit? And how do we actually figure out how high the monkey will be above the ground when the ranger hits the actual monkey, the target in this case? So what we know is that once the ranger fires a dart, it's going to follow a projectile motion path like this. Okay, it'll reach a maximum height, and then it'll come back down right here. And the monkey will be dropping at the same time the dart will be dropping. So a key idea is dart and monkey fall at the same rate. And of course we're ignoring air resistance, right? So the monkey's going to start falling as the dart starts falling. And we want them to collide here. This is their point of collision. And the trickiest part here is to set up all your coordinates and do your labels carefully, because you're going to be doing a lot of substitution. So we want the dart and the monkey fall at the same rate. And the other key idea is that the dart collision and the monkey collision must be equal at this position. So if we call, we label this as height, as the position of the monkey above the ground, and we call this Y monkey collision and Y dart collision. We want the position of the dart collision to equal the position of the monkey collision. So you must do an equation here, do the equations. And you're going to have times 2 because you have 2 coordinates, x and y coordinates. And then you do your equation for monkey free fall. And that will be times 1. Okay, you have a y equation only for that one. So you want to label this carefully. Call 8, let's say we call h the total height, y monkey collision to be this point right here. And then what you want to do is set up your kinematic equation to find out what the total, how to express the y monkey collision value in terms of all the other height positions. Okay, so a key, just to double check what I use for my notation, I call this y initial monkey and y final monkey. I label these 3 positions, and you use your kinematic equations to say that these 2 are equal. Now, one other thing that you have to note as well is that this position across here is the range of the darts. Okay. So your equations, what you're going to have is x dart equals so-and-so, and y dart collision will equal so-and-so. For the monkey in free fall, you're going to have y monkey collision will equal so-and-so. And then you set these 2 equal, and you have another equation for your dart, and you can solve for any unknowns based on the knowns that you have. In the actual simulations, you're going to be estimating these range values and the angles. Okay, so you're going to see which angles actually hit the monkey, and you're going to use those, and then you're going to find out what the range value is and what the height values are in the actual simulations, and see how those work out to figure out your time of flight in the actual problem. Once you know your time of flight, then you can use that to estimate any other questions in the problem. Okay, that's how you do those 5 simulations. Please refer to the handout I have on that. That has a lot more details. That's just an overview. And the very 2 last thoughts are part 2. We have our DIY experiments. Number 1 is just projecting balls or objects off a table. Okay, and we have some demos in another demo section for this lab. We have some slingshot. We're using elastic bands to propel balls across a table, and that gives us a consistent velocity. So this is a lot like cliff jumping Joey. So we get the ball to go off the table, and again we just want to measure the range and the height value. And what we do with the objects we're propelling off tables is we're dabbing it with a little bit of water and then putting paper underneath it so that we can mark the spot, and then we can measure this range and height. So use to find your V0. But the trick is, again, this is just all horizontal. Vx, we want it to be constant, and there's no Vy, so your angle is 0 degrees to begin with, okay? And the second experiment you're doing on your own at home is to use something that has another consistent velocity, like a dart gun, a hose, or some other object, but we're doing the same thing, and we're going to change our height value, but we're going to have our V0 going outward. Okay, not from a table, but we're going to have a height, and then we're going to go ahead and propel an object and measure our range and our height again. Okay. And then we're going to change our height value and then see how that impacts our range. Does it do this or does it do this? The second part is another projectile with V naught constant. A very important idea there. And you get that consistent velocity, and you can analyze the situation. You could find the time of flight. You could find some other information too as well. Okay, you could predict, what's going to happen at a larger height or a larger range as well. Okay, and that wraps up what this lab is about. So some other applications of this, if you look at your pre-lab, there's determining the pitching speed of somebody that's playing baseball. This is one that I actually did in the previous demo video. My son was pitching a ball, and what we did is we measured the range value, measured the height from which he pitched, but in that case, we actually had the ball land in a net a certain distance above the ground. So in that case, we were able to take the data of the different heights, the different positions, and the data from the range to find the pitching speed. So please see that problem. I have that posted. That's one application among many others. You can use a bow and arrow, shoot it out straight, and put a target that's a little lower from where you shoot it, and you can measure it that way, or same height. I mean, not exactly the same height. It's good to, you want to have some sort of difference in range there, so that you could solve for some other values. But the main idea in these ones is keeping that horizontal velocity constant and keeping the angle of elevation to be 0. Okay? So you will have a vertical velocity after this takes off, right? Remember, that's going to change and increase downward, but the horizontal velocity must be the same. All right, that's it. Have fun with projectiles, and hopefully you can apply that to all the other projectiles that you see and encounter in every day. All right, thank you.